In our first video, we studied the introduction to nanotechnology, and how these tiny materials are fundamentally changing our world. But to truly understand how green synthesis works, we have to step directly inside the labs of modern materials scientists. Before a single nanoparticle can be synthesized, researchers must map the raw biochemistry of their chosen plant extract. They conduct specialized screening tests to verify the presence of specific organic molecules. By running colorimetric protein tests, such as the Biuret or Bradford assays, they confirm the presence of catalytic enzymes. They screen for flavonoids, using alkaline reagent tests, and look for terpenoids, via the Salkowski method. These compounds are not just random nutrients. Flavonoids and terpenoids possess rich webs of aromatic rings and hydroxyl groups, which serve as the primary chemical machinery needed to reduce metal ions. By mapping this natural library first, scientists know exactly how powerful their biological reduction bath will be, before the main reaction even begins. When researchers look for the absolute easiest, and most efficient plant to use in the lab, they almost always reach for Camellia sinensis, commonly known as green tea. Green tea is considered a superstar in green nanotechnology because it contains an extraordinarily high concentration of epigallocatechin gallate, a powerful polyphenol catechin. This specific molecule acts as an ultra-fast electron pump. When a simple water-based extract of green tea is poured into a metal precursor solution, the chemical reaction doesn't take hours or days. It happens in mere minutes, entirely at room temperature. Because green tea requires no complex laboratory setups, no high pressures, and no toxic boiling, it has become the baseline model for scientists worldwide, proving that the most advanced nanomaterials can be brewed as easily as a morning cup of tea. Once the plant extract is ready, researchers introduce it to a solution of dissolved metal salts, like silver nitrate or gold chloride. This marks the beginning of a rapid molecular dance, known as bioreduction. The dissolved metal salt is swimming with highly unstable, positively charged metal ions. The flavonoids, terpenoids, and T catechins we identified act as natural electron donors. They aggressively transfer their excess electrons directly to the metal ions. This rapid shift neutralizes the electrical charge of the metal, transforming the ions into stable, zero-valent metallic atoms. As thousands of these individual atoms are neutralized simultaneously, they begin to collide and bind together, a critical chemical phase transition called nucleation. This is the microscopic birthplace of the nanoparticles, happening cleanly at room temperature. Building a nanoparticle, however, is only half the battle. Left completely to themselves, these freshly formed metal clusters would continue to crash into each other, binding tightly, until they clotted back into ordinary, bulk metal. To prevent this collapse, the solution relies on a secondary biological defense mechanism, known as capping. The long-chain plant proteins and biomolecules migrate rapidly toward the active metal clusters. They wrap entirely around the spheres, binding to their surfaces to form an organic shell. This shell acts as microscopic armor, exerting a powerful electrostatic and steric repulsion. Because the coated particles naturally push away from one another, they stay permanently suspended. This natural capping is what keeps the green nanoparticles stable for months, and ensures they are completely safe for biological use. With the chemical reaction complete, researchers move into the heavy phase of physical characterization. The first, and most immediate confirmation, is a vivid optical color shift. A clear silver solution will steadily transform into a rich, ruby brown, while a gold solution shifts into a vibrant, deep purple. To study this physically, scientists place the liquid inside a UV-visible spectrophotometer. This machine passes ultraviolet and visible light beams directly through the sample. Because nanoparticles have free surface electrons, they exhibit a physical phenomenon called surface plasmon resonance, absorbing light at highly specific wavelengths. By measuring the resulting absorption curve, researchers get instant confirmation. A clean, symmetrical peak on the graph tells the scientist that a uniform batch of nanoparticles has successfully populated the flask. While light absorption proves the nanoparticles are there, scientists must physically track which exact plant molecules form the protective capping armor. To solve this puzzle, they turn to Fourier transform infrared spectroscopy, or FTIR. The FTIR spectrometer shoots a beam of infrared radiation straight through a dried sample of the nanomaterial. When this light hits the sample, the chemical bonds holding the plant coating together begin to stretch, bend, and vibrate. Every distinct chemical bond absorbs infrared light at a precise, unique frequency. The machine translates these movements into a spectral graph, creating a unique molecular fingerprint. By studying the peaks and valleys on the FTIR spectrum, researchers can easily identify functional groups like hydroxyl bands or carbonyl chains, confirming exactly which protein successfully bound to the metal core. To take the organic characterization to the absolute limit, scientists frequently deploy mass spectrometry. This advanced analytical method allows researchers to identify the heavy, complex biomolecules with extreme precision, by looking at their molecular weight. The sample is vaporized and blasted with an electron beam, turning the surrounding plant molecules into charged ions. These fragments are then accelerated through a powerful magnetic field. As they fly, the machine measures their exact mass-to-charge ratio, separating them by their weight down to a single electron. The resulting mass spectrum allows scientists to read the exact chemical structure of the underlying metabolites. By pairing mass spectrometry with their previous tests, the research team gains an undeniable map of every single molecule participating in the green synthesis life cycle. Next, the investigation shifts from the organic coating directly to the inner metal core. Scientists must answer a critical structural question: are these metal atoms arranged in a chaotic mess, or do they form a perfect, repeating crystalline lattice? To find out, the nanoparticles are dried into a fine powder and loaded into an X-ray diffraction instrument, known as an XRD. The machine fires a high-energy beam of X-rays directly at the crystal planes of the powder. As the light waves strike the evenly spaced rows of metal atoms, they deflect and scatter, creating an interference pattern that forms sharp diffraction peaks. By analyzing these peak angles, and calculating them using a classic formula called the Scherer equation, researchers can determine the exact crystalline phase. They can instantly see if the metal forms a face-centered cubic lattice, proving the structural purity of their creation. To understand how these particles behave when suspended in liquids, researchers utilize two additional physical characterization methods: dynamic light scattering, or DLS, and thermogravimetric analysis, known as TGA. Inside the DLS instrument, a laser illuminates the fluid sample. The machine measures the microscopic fluctuations in light intensity caused by the random Brownian motion of the particles. This calculates the hydrodynamic diameter, which tells scientists the total size of the metal core, plus its surrounding water layer. Simultaneously, a separate batch is placed in a TGA furnace, where the material is gradually heated to extreme temperatures. By precisely recording the loss of weight as the organic plant shell burns away, TGA tells researchers the exact percentage of biomass wrapping the nanoparticle, providing an undeniable metric of capping efficiency. At this stage, scientists need to physically visualize what they have engineered. Standard light microscopes are completely blind at this scale, so researchers fire up the giants of electron microscopy, starting with the scanning electron microscope, or SEM. The SEM works by scanning a highly focused, high-energy beam of electrons across the surface of the nanoparticle sample. Rather than looking through the particles, the machine captures the electrons that bounce off the surface, mapping the topography with incredible precision. The result is a stunning, three-dimensional image that reveals the surface morphology. Through the eyes of an SEM, researchers can clearly see the shapes they have grown. Whether the plant extract has generated perfect spheres, sharp nanocubes, or intricate triangles. To look inside the very heart of the nanomaterial, scientists transition to the ultimate imaging tool, the transmission electron microscope, or TM. Unlike the SEM, which only maps the outer surface, the TM fires a beam of electrons completely through an incredibly thin layer of the nanoparticles. Because electrons have a wavelength vastly smaller than visible light, the resolving power of a TEM is truly mind-boggling. It allows scientists to view details down to a fraction of a single nanometer, revealing the fine internal grain boundaries and the exact thickness of the organic capping layer. By analyzing the TM images, researchers can map the precise size distribution of the sample. This ensures the batch is uniform, providing the definitive quality check required before these particles can be deployed in advanced biomedical engineering. In the modern era, physical lab benches are no longer working alone. The final frontier of characterization happens inside supercomputers, through advanced computational studies. Scientists use quantum mechanical simulations, such as density functional theory, to model the exact interactions between the metal atoms and the plant extract molecules. These computers simulate how a single flavonoid molecule approaches a silver ion, predicting the exact thermodynamic energy required for the electron transfer to happen. By combining physical lab data from FTIR and TEM with these virtual computational models, researchers can predict nanoparticle growth, shape stability, and surface reactivity with flawless accuracy. This powerful alliance of biology, physical machinery, and computational code is transforming green nanotechnology from an accidental science into a precise, highly engineered revolution. From basic plant extracts to high-energy electron beams and supercomputer simulations, green nanotechnology proves that we can build the future while protecting our planet. If you found this complete 10-minute masterclass scientific deep dive valuable, please smash that like button. Subscribe to the channel, and let us know in the comments which analytical tool you find most impressive. Thank you for watching, and we will see you in the next video.